Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen, all of the reviewers, the committee, and all Borobudur International Symposium 2024 participants. My name is Bela Amelia. It is such an honor for me to speak on behalf of the researcher. Let me begin by giving you a warm welcome in this seminar with our research entitled Minimizing Distortion in Flux Core Arc Welding of A36 Steel by Preheating and its Effects on Weld Mechanical Properties. The first author in this research is myself, Bela Amelia, as the presenter. The second author is Professor Mochammad Nur Ilman from the Faculty of Engineering, Universitas Gadjah Mada. And the third author is Mr. Nur Akhmad Triwibowo from the Institute Teknologi Dirgantara Adi Sucipto. Welding, widely used in shipbuilding, creates strong, efficient joint but faces issues like distortion and residual stress on thin plates. These factors weaken the structure, making it prone to fatigue and failure under dynamic loads. This requires welding to have strict procedures to prevent failure. One of which is the flux core arc welding method that is commonly used in ship welding. Although distortion can be prevented, it can still cause residual stress in distortion. For this reason, the flux core arc welding method is combined with the preheating method. Bokhol and Da Silva reported that flux core arc welding procedures better penetration than GMAYY because it doesn't require large heat input, thus providing better stress distribution around the weld joint. According to Yorioka, preheating is necessary to prevent cold cracks in steel welding. Subsequently, Zabaruddin, in their study, reported that preheat produced a more homogeneous temperature distribution and significantly reduced residual stress and local deformation. Consistent with this report, Tariq and Jawad also reported that preheating ensures a slow cooling rate so that residual stress can be distributed widely and reduce critical stress. In this research, the material used is ASTM A36 steel plates welded using flux core wire A71T11, with its chemical composition is given in Table 1. ASTM A36 steel plate with dimension of 300 millimeters times 100 millimeters times 3 millimeters were welded with a V-groove with an angle of 30 degrees and a gap of 1 millimeters along 300 millimeters. The welding was conducted using automated flux core arc welding to maintain consistency in data collection. The welding parameters and consumables detailed in this table. The first specimen was welded without any treatment called as welded, as shown in figure 1a. The other specimen underwent a preheating process using two electric band heaters placed 20 millimeters on either side of the weld joint, as shown in figure 1b. Preheating temperatures of 100 degrees Celsius, 200 degrees Celsius, and 250 degrees Celsius were selected to assess their effects on the distortion and mechanical properties of the welded materials. The heaters were used to prevent extreme temperature gradient and control the cooling rate. After preheating, welding was performed along the V-groove joint with temperature monitoring using a K-type of thermocouple. After welding, the distortion for each welding condition was measured along the plate at 10 millimeters interval using a dial indicator evenly distributed across the entire plate. The measurements were taken in the longitudinal direction. The preparation for metallographic observation involved taking a cross-section of the weld metal and each using 2% of neutral reagent. Microstructural observation is to examine the change in the microstructure along weld metal, heat-affected zone, and base metal. The weld hardness was measured using Vickers microhardness at 80 points with a center-to-center distance of 500 micron. A load of 300 gram force was applied with a dwell time of 10 seconds. Two figures in intention diameter was measured based on diagonal value as described in equation 1. The figure's hardness value was calculated using equation 2. and the tensile test was performed along the longitudinal direction on the weld following STM-A8 standards. This test provided the tensile properties, including yield strength and ultimate tensile strength. As a result, the preheating process carried out before welding shows an increase in temperature, reaching the higher peak of temperature of 780 degrees Celsius. This occurs because preheating causes the material to reach a higher temperature. Preheating helps reduce the extreme temperatures gradient between the weld area and its surroundings, allowing heat to be distributed more evenly. For distortion, these results show that increasing the preheat temperature reduces welding distortion, with the best reduction observed at 250 degrees Celsius. This is because preheating retains heat for a longer period and prevents rapid cooling, thereby reducing distortion. Also, preheating causes microstructural changes in the weld metal region and heat-affected zone, with the amount of varied being increased with increasing preheating temperature. And linear with the microstructure results, an increase of the amount of varied indicates that hardness decreased with higher preheat temperatures applied. The slower cooling rate allows time for hydrogen to diffuse out of the weld metal because the formation of hard microstructure, thus minimizing the risk of the hydrogen-assisted cracking. And as a result, the ultimate tensile strength of conventional wet metal, typically 629.9 MPa, decreased to 547.6 MPa after preheating at a temperature of 250 degrees Celsius. However, this reduction in strength is compensated by improved ductility. For the conclusion, in this work, Flux oil welding of ASTM A36 weld joint under the effects of two in-process treatment, namely as welded and preheat treatment, have been investigated, and the following conclusion is: first, the increasing preheat temperatures reduce welding distortion with the best reduction at 250 degrees Celsius. Second, preheating also causes microstructural changes in the weld metal region and heat-affected zone, with the amount of varied being increased with increasing preheating temperature. And last, the ultimate tensile strength of conventional weld metal, typically 629.9 MPa, reduced to 547.6 MPa after preheating at temperature of 250 degrees. But this strength reduction is compensated by its improved ductility. This is the end of my presentation. Thank you for your kind attention. Assalamualaikum warahmatullahi wabarakatuh.